Hi! One of the questions I most commonly receive, especially on my latest video where I unbox some extreme magnets, is: with the iron in our blood, isn't it dangerous to handle such strong magnets? In this video, I'll show you how blood reacts to a magnet and try to explain why it reacts in such a strange way. This time I will handle powerful magnets and blood. If you don't want to see blood, you sort of picked the wrong video, but I'll tell you when to look away, okay? Alright, first of all, is there iron in our blood? Yes, there is, but not as solid metallic pieces of iron like these filings. If it was, we would definitely be in trouble near a magnet. Let me just demonstrate with water and red food coloring. Without iron particles, the blood runs smoothly through the tube and past the magnet. However, when I add solid iron particles, the iron builds up and forms a clot near the magnet in the simulated blood vessel. This would give you a bad day. Luckily, as mentioned, iron is not present like this in real blood. Instead, it is part of a big molecule, the metalloprotein hemoglobin. Hemoglobin is the red part of red blood cells, and it is responsible for carrying oxygen around your body and removing carbon dioxide from it. It is a very complex molecule. For comparison, around half of our blood is just water. A water molecule is made of 2 hydrogen atoms and 1 oxygen atom, giving it the chemical formula H2O. A simple and easy to remember molecule. Hemoglobin, on the other hand, is way more complicated. It is made of, hold on, let me get this right, 2,952 carbon atoms, 4,664 hydrogen atoms, 832 oxygen atoms, 812 nitrogen atoms, 8 sulfur atoms, and 4 iron atoms. 4 atoms. Our blood isn't exactly crammed with iron. For an average human body, the total amount of iron is around 4 grams with 2.5 grams in the blood. But does any iron content mean that the material will be magnetic? Let's test some common materials with different amounts of iron content. First up is matches. These contain a tiny amount of iron as ferric oxide, an impurity in the match head. Not enough iron to have them stick to a magnet, but on a sensitive water bath they are slightly drawn towards the magnet. Now, if I do some chemistry to them by setting them on fire, something changes. There's the same amount of iron atoms in the matches, but the ferric oxide was reduced to pure magnetic iron in the fire. This gives us a clue. Iron atoms don't always have the same magnetic properties. It depends on the whole molecule. Even this fork, made of stainless steel, which is mostly iron, has different magnetic reactions depending on which end I test. The elements in stainless steel can form different crystalline structures. The cold work done to the tines changed the crystalline microstructure slightly, making them more magnetic than the handle. Still not very magnetic, even though there's a lot of iron in this fork, so much more than in any matches and blood. Alright, based on these tests, can you guess how the blood will react to a magnet? This is where you should look away if you are sensitive to seeing blood. I'm about to open a bucket with 3 liters of it. I don't like to bleed, so I went to the local butcher and bought some food-grade blood from a pig instead. Perfect. Let's test it with the monster magnet right away. This magnet is insanely strong, but I don't see any movements in the blood. Let's use a small amount on the revealing water bath. As a control test, I will test the empty container first. Seems neutral enough to be negligible. Time to fill it up without making too much of a mess. Here we go. Did you guess how it reacts? Not what I expected. It seems to be repelled by the magnet. I honestly have trouble holding this 12 kilograms monster steady, so let's confirm with the lighter sphere magnet. Yes, the blood is definitely repelled by a magnet. This is called a diamagnetic reaction, but how is this possible with iron in the hemoglobin? Well, magnetism is a quantum mechanical effect, scaled up to be noticeable to us. Quantum mechanics, however, does not compute well with our everyday logic. Very simplified, magnetism is an interaction between unpaired electrons moving in the materials. Paired electrons will sort of cancel out their magnetic dipole moment by having opposite spins in the atoms and molecules. Only unpaired electrons will have a net magnetic moment reaching beyond the atoms and molecules. So, roughly speaking, we can determine the magnetic reaction of an atom, molecule or crystalline structure by counting the number of unpaired electrons in it. In hemoglobin, the number of unpaired electrons in the iron atoms actually change, depending on whether it is oxygenated or not. The iron atoms in deoxygenated hemoglobin each have 4 unpaired electrons, making it paramagnetic and a little attracted to a magnet. The iron atoms in oxygenated hemoglobin turns out to have only paired electrons, no unpaired. This gives oxygenated hemoglobin a diamagnetic reaction. It is repelled by a magnet despite the iron content. The ratio between oxygenated and deoxygenated hemoglobin is typically like shown on the screen. Most of the hemoglobin in our blood is in the diamagnetic oxygenated state, being repelled by a magnet. The water making up half of our blood is also diamagnetic. So after all, it does make sense that the blood is repelled by a magnet. The conclusion is clear to me. Do not worry about the iron content in your blood near a magnet. Even the strongest magnets, like the superconducting electromagnets in MRI scanners, will not be a problem. The iron is not in a ferromagnetic state in the blood. Hope you learned something new in this video. I certainly did researching for it, and speaking of learning, I've got some good news for you. I found that the best way to learn more is to get my hands dirty and do some interesting experiments, some of which I have shared. But you may not have access to, for example, big neodymium magnets, so what else can you do? My new sponsor, Brilliant.org, is a problem-solving website that teaches you how to think like a scientist by performing your own thought experiments. What I like the most about their lessons is that they guide you through the thinking step by step, so you can work out the stunning conclusions on your own. I'm a fan of science and always like learning more about it. If you are like me, then I highly recommend you go to brilliant.org/brainiac75 and sign up for free. As a bonus, the first 200 people using the link will even get 20% off the annual premium subscription. That allows you to do more crazy stuff without any safety warnings from me. Thank you for watching. Hope you liked the video enough to click thumbs up and maybe even subscribe if you're new here. See you in the next one.